Hello, everybody. As you can see, there's a little bit of technical difficulty. A little bit of technical difficulties here. I managed to mess up the OBS settings when I was working on them yesterday, trying to get things put together, which of course is exactly what I wanted to have happen. So, this right? No, this is not right. Oh, this is great. This is just wonderful. So, let's see here. Cancel this. Cancel that. I guess the good news is that it looks like no one has tuned in yet. So I guess that's a good thing. I'm kind of concerned that I can't find some of this stuff, though. Ah, there we go. This is what I wanted. Yes, this is what I wanted. So I should be getting ready in just a minute here. Like I said, unfortunately there we go. That looks much better. We want to move this over here, which should get in there just right. Yeah, so unfortunately, I was trying to get things set up so that I could do some video game streaming when I'm not working on all this stuff. And unfortunately, I hit some buttons wrong, and OBS decided that my assumption was that a profile in OBS was all of the settings. It turns out it's only a subset of the settings, which does not include the scenes, which are what you're seeing. So, I mean, at least I did not manage to delete all of my all the graphics or something like that. So it's not a total loss, but it did mean there was 5 minutes worth of rebuilding that had to be done just now. And even then, it's not perfect. It's, workable, but not perfect. So where are we here? If we SSH back into this thing, apparently I still have the same IP address. I thought we set keys for this already. We set those on the other system. Oh. I think the enter resize there. No. Resize that to 80. Resize this one to 80. And now I need to come in here and resize this chat box so that that also lines up. And once that's done, it's pretty reasonable, I think. Well, at least it's good enough for us to get started. Yeah, there we go. That looks just fine. So, while I've been working on this, what are we actually doing tonight? So tonight's going to be the last of the, well, it's probably going to be the last, or close to the last, of the CPU errata things. So we've been looking at a Intel Skylake bug. We've been looking at this for almost a month now. Unfortunately, I haven't been getting much in the way of progress. Like, most of it has been just mostly spinning around and not getting anywhere. So, last Wednesday, we started writing some code, and then my system decided that, let me move this a little bit closer so we get a little bit better sound here. Where was I? So we started writing some code, and then my computer decided that I probably didn't actually want to be using the internet today, and the router crapped out, our internet died, and yeah, that stream ended quite a bit early. So in the past week, I've managed to score quite a bit in the way of technical difficulties, which is super exciting. But where are we? So yeah, let's get rid of this. So the short version of this is that we want to set up multiple threads that look as similar as possible to the code in... I'm sorry, I'm blanking again here. We want this to look as similar as possible to the function that is believed to have been causing the OCaml crashes related to this. So in just a second, I should be able to pull that up here. Downloads, the binary ninja. Oh, right. Seems like every time I do this, I forget that I need to manually start an X server because I'm using Windows. And it doesn't really make a ton of sense for me to be running that all the time. At least that's what I think. It seems a little silly to constantly be running a... X server if I'm not going to use it. It just adds more surface area. I want to give you not that screen. This screen? This screen? No, this screen. Why are you not giving me that screen again? Well, in that case, we can switch which screen we're using for this. That'll work reasonably well, at least. So that one. Okay, so where were we in here? We want to go to... Try to remember what the function's called. Slice something, right? Sweep slice. That's right. And in sweep slice, we're coming over here down and to the right a little bit. And we want to capture from here all the way through where they use AH right here, and then loop around. So we want to get at the very least that entire path and all of the instructions we can. Plus, we want all of this to be valid, assuming that we can set that all up. So we want these memory accesses to be in different areas. In particular, we want them to hit different pages if possible, because we're trying to make the... oh, and I should fix this a little bit so that it isn't... So that goes there. We're going to move this around so you can actually see what I'm doing. That looks good. But yeah, we want to move things around so that it actually looks like our the OCaml that we think is triggering it. And so the really quick version of this is we're going to start out here. Well, first we need to finish out this code. So this code, for anybody who doesn't remember or wasn't watching last week, is the OCaml sweep slice code. And essentially the supposition here is that there's this relatively tight loop, which when we hit, here, I can even mark these blocks, can't I? When we go through, not a fan of color, but that'll do. Highlight block, highlight block, highlight block. Do we need to, yeah. Highlight block. So if we go through those blocks, and that's going to loop around again, right? Yeah, that loops around. So if we go through all of those blocks and we write some assembly that looks pretty similar. So we're going to load RDI from one memory location. We're going to then load it, we're going to compare it to another memory location. and basically go through all of these blocks. We want to hard code it so that every time we go down this path, and then this path, and then this path, not necessarily hard code it, but we're going to cheat a little bit, because RDI we fully control, and we fully control whatever limit is. So we can set these to be values that we know we're always going to go down this path. In this case, RBP is set. R12 is not set in this loop at all, so we're fine to make it whatever we want it to be. We're then gonna, compare here. Basically, we want to make this such that we will always go down this loop. We do this in this tight loop over and over and over and over again, and we're going to watch for differences. And at least the idea here is that that should trigger something different for us. We don't know what. All we know is that, so I guess it was 2 weeks ago now, we went through and we tried to collect a whole bunch of these, I'm blanking on words again, core dumps. I ran these for about a week. Downside is that the core dumps end up being very large, because as far as I'm aware, there is not a small test case for this. Now, I could be completely wrong. It's been, I've done a little bit of research into it, but everything that I've seen, there's not a public example. This should be on top of that. There we go. There's not a public example of somebody actually doing anything with this in terms of reproduction. All we have is there's a microarchitecture patch, which conveniently nobody really knows how to tell what's going on inside of it. The rumor, as I've heard it, is basically that there's a handful of people at Intel that understand how they work, and that's it. There's some people who have an idea of how to see what's going on with it, but nobody else really knows what's going on with them. So, we can't look at the patch to figure out what changed. And the only test case that I've been able to find, the only example anyone that I know publicly has talked about, is this OCaml compilation task. So somebody about a year ago was writing some OCaml code. They went to compile it on their system, and it would periodically crash on them. So they went back and forth and back and forth and back and forth. And one of the OCaml developers reached out to Intel because they tried everything they could think of. They couldn't find any problems at all. So they reached out to somebody at Intel. Intel took a look at it, and it turns out it actually is a CPU bug. That, again, the theory here, because I cannot verify this, but the theory here is that these two instructions right here are the problem. That when they use this AH register and the RAX register inside a tight loop, whatever a tight loop is, that is going to trigger something happening in another thread on the same core. All of this ends up meaning it's going to be complicated and hard to trigger. But ideally, we'd be able to do this, write some assembly, make it do the same thing, and see some sort of result. Now, the first week or two that we tried, the first couple of streams that we did on this, we poked at this, we tried to make this work, we tried to make this work, we tried to make this work. It did not work at all. We wrote some assembly, we wrote some C. I think the first one we wrote a bunch of C to try and make the same thing happen, and the compiler did not cooperate at all. We couldn't get it to emit stuff that was similar enough to be usable. So then we switched and we decided, okay, if we can't do this in C, we're just going to write some assembly. Let's ignore the playing with compiler optimizations until we figure out what kind of code will emit something that looks like this. Let's just write the assembly ourselves. And so we went through, we wrote some assembly, we threw it all in there, we let it run, and nothing happened. So, after that, I went back and forth. I ended up getting a hold of one of the OCaml developers, and that's when we were able to get this test setup running. Basically, I have a laptop that I know does not have the patch, because I'm able to run their OCaml compilation task and get crashes. which is great. So the theory here was that, okay, I can get crashes. Let's do what, people do all the time. I know that doing this thing is going to cause a crash. If it causes a crash, I can get a core dump. I can take a core dump. I can, open that up in GDB. I can figure out exactly what's going on, right? Well, no. It turns out that each of these core dumps is almost half a gig. In some cases, they actually were a gigabyte in size. Because when they go to make their OCaml compilations, they're generating these giant ASTs for this file. They've got all sorts of things in memory. So when it goes to crash, the OS conveniently goes, here is all of memory for us to pile in there. Because realistically, we probably need that if we were starting from nothing to figure out what was going on. But the end result is, my poor laptop that's vulnerable to this, it's only got space for maybe 200 of these if I, played with storage well. So we got a bunch of these, and we went through and we took a look at them. We wrote some... it's actually an interesting stream if you want to go back and watch it. I believe it was like... I can pull it up here. Number... whatever this one is, right? Yeah. So it's this one right here. If you're going to go back and view it. Basically, we wrote... actually, why am I doing it this way? I could show you guys. Look at that. Basically, we wrote GDB Python. So you may or may not be aware of this, but it turns out that... oh, come on, there's got to be a good example in here where I can actually show the code. But GDB has a full Python interpreter embedded in it, and so we took advantage of that, and we managed to write a whole bunch of this Python to do some basic analysis of it. And of course, now I can't find good examples of that. But things like this. We took everything, we output it to a database, we did some analysis of it. Because the theory here, at least my theory, was that if we got a whole bunch of these and took a look at it, we should be able to find out that this is where the crash is happening. So, hi, Tim. So what we're doing here is about 2 months ago, Intel... oh, I don't have the boxes for it. So about 2 months ago, Intel released a CPU microarchitecture update. And they fixed several bugs in the Intel Skylake and Kaby Lake processors. So what we're trying to do here is actually reproduce that bug. So the reason this is all interesting is because it turns out one of these bugs, the SKL 150, and let's throw that in here real quick. Sorry, I'm a little bit off on my stream layout stuff right now. I accidentally killed all of it last night. So SKL 150 analysis. So there's this Intel Skylake bug, which we want to try and reproduce, because at least as far as I'm aware, the only time anybody has publicly shown anything about it is some of the OCaml developers, because there was a case, looking at the bug report, it looks like back end of last year, beginning of this year, there was a test case that somebody found that if you compiled this OCaml code on a Intel Skylake processor, it would crash sometimes. The compiler would crash. And at other times, it would output the wrong code. So, that's really interesting. It was reproducible, but only sometimes. And so these developers went back and forth and back and forth and back and forth. And if we actually, you know what? I can actually pull it up here, can't I? Rather than just talking about this. we have the technology. Where are we here? Did I not? I didn't copy it into this link. Sorry. I'm trying to grab this link from the other streams, but apparently I've been a little bit lax on actually copying it over. But so this is the 6th iteration of this, I believe. Oh, there it is. So this right here is the dev report, or the bug report from the OCaml developers. And this right now is the 6th week now that we've been going after this, trying to reproduce it. Because it turns out the line right here about, where is it? Under complex microarchitectural conditions is much more important than I was guessing it would be. My thought was that, oh, I'm going to put in this and AHOXFC, I'm going to write it to memory, and bad things are going to happen, right? Well, it turns out it's not that easy. So tonight's stream is now the, what is this? The 6th time we're going to go after this. And at least the idea is this function right here, the OCaml developers managed to verify that this function is the one causing the problem. And they were able, the way that they were able to do that was they found out that if they compiled the compiler with -01, to optimize to the whatever the 01 level does, it would not ever crash. But if they went to 02, it would crash. So this whole search through the entire code base for the compiler, and eventually found out that this function, they were able to exclusively compile this function with 02, or 01, and the entire rest of the code base with 02, and it didn't crash. And then as soon as you compiled this function with 02, it would crash. So this was all back in January that they figured this out, and they said, you know what? This is bizarre. We don't know what's going on. We know it's bizarre, and we know that it only happens on one processor. So it must not be our problem. Well, they didn't say that, at least not that I know of. But apparently one of the, primary developers, one of the core developers or something, knew a guy at Intel. They got to talking to Intel about it. Intel goes in the tank, and 3 months later, Intel releases this update. And nothing happens for about a month until one of the OCaml developers just happens to say, oh, maybe this is relevant. And it turns out it actually is relevant. If you put the microcode update for the SKL 150 bug on an Intel Skylake processor, it goes away. So we know that this is the bug, well, this is the CPU bug that causes it. We have a description of how it works. And I have code that should trigger it. Unfortunately, the easy examples never triggered it. So tonight, we're going to be going through, and I'm going to write something that is hopefully nearly identical to this. And that's what this code on the left is going to be. So just to run through this real quick. So let's actually run it real quick. So cd projects, this, we're on test 2 now because our test 1 failed miserably. So it's going to say working. It's then going to start up, what is it? We're going to start up 16 threads. And for each thread, we're going to call this thread1 function. Now, you may notice the thread1 function is an extern, which basically means that we're going to use NASM and write in raw assembly whatever we want here. And the idea here is that, well, we should be able to then have code that works. So, with that said, it's been a couple weeks since I took a look at this, and it would appear, at least, that this code is kind of broken right now. Because if we run this, so let's start with this. So we put out working. We then do this right here. So we're declaring a threads int. We're creating an array of threads int. And each of those thread ints is what is going to be passed in to each of the thread functions. So we call ending now here. Does that happen every time? No, it does not happen every time. So why are we segfaulting here? Oh, because I'm dumb, right? No, this will loop forever, so that's fine. Well, let's verify that. I should always assume that it's not that I'm not being dumb. I should assume that, you know, this code isn't the best code in the world. It works. Hopefully it works at least. So I can't knock it too much, but this broke. I want to set new. I want to set auto indent on because I am not an animal here. We make passing argument 3 from incompatible pointer type. I don't think I care. And yeah, it wants a void star instead of an int star. Okay. We can fix that real quick. Void star. Oops. Ta-da! And we segfault, like right away. Every time we segfault, okay. We are in start loop. So unfortunately, I'm doing this on my laptop, which has a relatively fresh Ubuntu install on it, so that we could actually reproduce this, which means all of my environment is completely wrong for this. I don't have any of my GDB set up the way that I want it to be. I don't have anything at all set up right. So we are comparing RDI to the value in RDI. Because RDI is the... Why on earth are we doing this? This is, of course this is crashing. Puts is causing that to have problems. That's fine. Push RDI, pop RDI. Okay. Close that. We want to make this and run it. That's a little surprising. We also want to come in here and we want to do int continue, int cont, because that's easier to spell. No. This is the downside to doing things this way. Cont is equal to 0. So because of how I'm doing this, oh, did I not? Oh, I don't need a semicolon there. So why did we break? So printf. Yeah, that's fine. This is gonna get old fast. Printf percent I failed is equal to this instead. I is I, and then we also want thread ints I. So what was it? And what should it be? Does not equal that. I keep doing that. Okay. 414141 does not equal 41. Oh, I'm being dumb with my Boolean here, aren't I? That seems like what I want to see, right? So each of our threads runs, they also all end, and they bail out. Which is kind of what I expected to see here, that if we run all these, that they will end up failing like this. So that's good. Well, good in that it the code is doing basically what I expected to do. But it isn't good in that, well, actually, no, that's not true. That's exactly what I wanted to do, so that's great. So I did this. So now we need to come back here, and we need to make this code look more like the code that we had from the Skylake stuff. From the OCaml stuff. So let's go back over to this. So what are we doing here? The first thing we're doing here is we're comparing. So we're going to read a value out of memory and put it into RDI. So let's think about how to do this real quick. So we know that RDI points at AAAA or BBBB or CCCC, so we're going to be able to read that out. We can then do this comparison. We want to flip this comparison though. So let's do that real quick. So we're going to do a move, compare, jump below or equal. This goes away. We're coming back over here. Whoa. Okay. Where? Oh, I'm over in that. Come over here. There we go. Okay, so the start of our loop here. What did we say we were doing? We're doing a move RDI reading out of it. So to start with, let's say we're going to do a move. Let's use R13 for this. I swear, I need to type slower so that this stops happening. Move RDI keyword R13. So this will load 4141 and 41 out of that. Actually, this is going to load 414 and 4141 42 42 42 42, not 4 ones, but that's good enough. We then went to compare this. Let's actually compare this to a value that we can say will always be above. So limit, right? Or we always want it to be below this. Why? So we want to do limit is going to be db ox 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. Okay, so we have that. So there's going to be a constant there. We're going to compare that to a constant, and we're going to jump above or equal to lock 2. Now, we're going to jump above. So if RDI is above limit, which it never will be, we want to jump to limit. Sure, why not? or end. That sounds fine. Then for block 2, we're going to do a move racks. So this right here, I'm copying verbatim the code from the assembly. Set new move RDX racks, move RD, or I'm sorry, shift right RDX OXA, move RBP RDX RDX, LEA RDX RDI plus RDX times 8 plus 8. Not RBP. Move keyword a thing. RDX. Move RDX racks. Add RBP R12. And EDX OX300. Move R12 RBP. And then we're going to jump equal to end. Okay, so we have all this. And the first thing that I see here that I know that we need to fix right away is we actually need to change the way we're doing this. Because we're going to need to pass in more stuff than what we're currently passing into this thread. So let's go back to that. So instead of doing this, like instead of passing in one thing, we're going to pass in a struct. So we have a struct args, and we're going to have a void star a semicolon, I think? Void star b. I think that's right, the right syntax. Going to yell at me in a second if it isn't. Make. Okay, so that's right. So we want to, for each of these, instead of having thread ints, we're going to have, yes, we can have thread ints. That's fine. For each of these, we're going to populate one of these things. So struct args star args is equal to malloc size of struct args pound include malloc.h. So we populated this thing. Args a is equal to and thread ints I. Args b is equal to malloc ox 21,000 hex. So why are we passing in that much memory? So the idea here is we want to be able to address different regions inside of this memory that is readable and writable, that is going to be non-contiguous. So in the assembly, they've got several of these symbols that we have names for that they're reading from. And I don't know if these are going to end up in the same cache block or not, but I can make sure that they don't end up in the same cache block by reading from one page and then reading from the next page and then reading from, like if I store each of them in a different page, then clearly we're going to end up with, something interesting. So we're passing all of this in. So back to our assembly. So to start with, RDI is no... Oh, I'm sorry. We haven't actually switched to doing that, have we? Args. Right. So now we're passing in this. So the first thing we want to do is we're going to... Oh, no. We push RDI. Move RDI keyword RDI. Is that right? So struct, we're pointing to a struct here. We want to get the A member out of it, which would be the first member. So it'd be that. Yep, that looks right. So we do that. You know what? We're not going to do this. Let's just pop R13. It'd help if I could type, wouldn't it? You know, I also never actually remember GDB test run b main run. So yeah, I should be able to go all the way up to R15 without a problem. Yes, this is how I was checking to see how many registers I had available. So let's actually just put this in R15. It's the highest one. This is a pointer to R space. We're going to do a move R14 keyword R15 plus 8. So this is going to be the B variable. So R14 points at a big block of memory that we're going to be able to address into to get whatever it is that we want out of it. So that should work. Well, now that I say that, the code isn't getting a... I don't think that's going to matter. So we have R15. R14 is the big block. We then want to set up R13, which is going to be our camel GC sweep HP. If you're not familiar with NASM, the semicolon is a comma here. So R13 is going to be R14, or let's do a LEA here. LEA, R13, R14, R14 plus, actually just R14 is fine. And then limit. We can't use R12 because R12 is being used in our loop, but we actually care about that. So LEA R11, R14 plus OX 1000. So we're doing this to make sure that these two pages, so these two addresses are in different pages, so they have to be in different cache blocks. So regardless of what is causing this, we know that they're going to be in different cache blocks, and we should be able to say that because of that, whatever's going on should be the same. So we have that. So this is the sweep. Okay. So that should work. And instead of R13 here, that is the camel GC sweep HP. This is R13. We're reading that in to be RDI. I'm not sure if we care what it is, right? We'll backfill this and make it actually make sense, but and limit is R11. And so we need to make sure that R13, or the pointer at R13, is always lower than whatever is at R15. So we're going to move keyword R11 OX 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have that. So now, regardless of what... Oh wait, it's above or equal, right? Above or equal is the signed version of this. So we don't actually want this, we want that. Right? Above or equal is signed, so there cannot be a there are no values above this, and the only value that is equal to this is equal to this, which should be fine. So we have that. So we read out of R13 into RDI. We then read out of R11. So R13 should be zeros because we haven't initialized that memory. We're going to actually fix that. At some point, let's put in some filler here. Move keyword R13 1. We'll fix this later when we figure out what we want it to be. So we did that. We compare them. This condition will always come down here. We're now in block 2. We're going to actually try and read out of that. What happens when we try and read out of that? So we read out of that. We put the value into racks keyword. We move that into RDX. We shift that by 10. We move that into RBP. And then we're going to read another value out of this. So both of these are based off of RDI. So RDI is some list of, or it's some buffer that we're going to index into. And the first value is, we move it into there, then we shift it by 10. So we lop off the bottom 10 bits. We then multiply that by 8. So we're shifting it back over by 3 and adding 8. So we've shifted by 7 and made it page aligned and added 8 to that. And that is going to be the offset into this thing. Okay. Well, so what's that doing? That's basically getting the number of bits. So if that's a bit offset, that would make sense. We then knot it. Well, actually, let's go forward a little bit here. So we're going to make sure that in order for us to go on to block 3, we need to move app. Okay, Intel x86 manual. Because I don't know about you, but I don't actually know which of the... Let's pull this up so we can all take a look at this. We've brought plenty for the entire class. I don't for the life of me remember which flags get set by move and how they get set. Move affects no flags. This and will set the flags. That's the worst. I hate it when compilers do that. I'm sure there's a good reason for it, but it makes it a lot harder to read. That this instruction causes the flags to be set. This one acts on them, and there's an instruction in between. For not really any good reason. But where were we here? So, coming back to this, that could go away. So, EDX cannot be, or EDX has to be, EDX cannot be 300 hex. And we save off, so this is not a thing, this is R13. EDX comes from RAX. RAX comes from whatever was in RDI. And as long as that is not 300, we'll be fine. Okay, I can live with that. So RAX is the thing that is there. So at least for now, it should be safe for this to be, let's say R10. Oops. So R10, move R10 keyword R15. So this is going to be the R10 is the pointer to our string. So we're going to do some calculations on it. We're going to write it to R13. We then move that string, so AAA, BBBB, into RDX here. We make sure that it's not 300 hex, which it can't be unless we've done something terribly, terribly wrong. And R12. We don't care. We're loading R12 here, which is fine. On to the next block. So the next block is going to be a compare RDX OX 200. Jump not equal to block 4. And we do want to follow this branch. So the immediately next instruction will be an int3. So if we ever hit this, right, we want to immediately crash. Which is fine. We're then going to have a block 4 here. This is and AHOXFC move keyword RDI racks, jump to block 5, int3 here again, block 5, and this is a test RBP jump greater. What does a jump greater do if you're comparing a register to itself? Start loop. Okay. So that's that. This is rough. So this should have the same, in theory, and by theory I mean my loose guesstimate here, this should have the same complex marker architectural conditions as the sweep slice code at the point where the AH and RAX registers are both being used. So, coming back over to the Intel manual, function home, page down, I need a jump conditional. Jump if condition is met, and I need a jump greater than. So jump if greater, which is the 0 flag, and sign. So I'm going to write some notes here. So ZF is equal to 0, the sign flag is equal to the overflow flag. And if we come back over here, we are doing a test. So back up here, how does test set those flags? We're doing a logical compare. Flags set. So the overflow flag is 0, which means the sign flag needs to be 0. The sign flag is the most significant bit of when we AND these two things together. So the top bit of RBP can't be set. And the 0 flag needs to be 0. So the 0 flag needs to be 0, which means RBP has to be 0. Thanks, compiler. I don't know why you used a jump greater than there instead of just a jump equal or something. So RBP has to be 0. Where did RBP come from? RBP came from here, where we add R12 to ugh. Well, this is going to be tricky. So, oh, and we save it off. Awesome. So, if we come up here and we say, at line 29, move R12 0. We're going to make it easy on ourselves, right? R12 is 0. How do we calculate RBP then? So as long as R12 stays 0, They can't be the same thing. Ugh. This is awful. Right? You know what? Hopefully this doesn't matter. Because, I mean, hopefully these are going to work out somewhat reasonably. So the only other thing here is we need to make sure that R12 and RBP are... As long as R12 and RBP are always 0, we're fine here. How do we make sure that RBP is going to be 0? So RBP is not... It's knotted there. And RBP is... So it can't be 0. Awesome. Do I have to do math here? This sucks. Okay, so... No. Come on, guys. We talked about this earlier, that this is comparing EDX to 300 hex, not R12 and RBP. So EDX comes from RAX, which is what RDI points to, which is the string that we passed in. Right? That sounds right. I think that's right. So that should work. Okay. That was a lot of raw assembly to write. Let's see if it just compiles. Ah? Oh. Line 62, instruction expected. Oh. Signed D-word immediate oh, right. Crap. Move R8. So I can't use stuff like that. I have to do stuff like that. Okay. 43. Type mismatch in operand sizes. Well, so in Binary Ninja, this did not have an operand size, and it works. What? So we're in block 4. So RDX. How? What? How did that happen? Okay. Am I crazy here or something? We compare RDX to 200 hex. We then So we do write to RDI. What we're writing to RDI is RAX. RAX came out of Am I taking crazy pills here? Like, I feel like I'm taking crazy pills here, right? So RAX comes out of RDI. It isn't set here, it isn't set here, it isn't set here, it isn't set here. No, 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 no. It will be modified here, written here, and we loop. Oh, oops. There we go. RDI is what is at R13. And what is at R13 is R10. And R10 is the... That's not how computers work at all. There is absolutely no reason why this should happen. Because R10 should be a pointer to R10 should be a pointer to our string. So we're comparing, we did this comparison, and we said that they're equal because RDX is somehow 200 hex. Oh. Well, how'd the high bits get set? Okay, you know what? B thread 1. Yes. Okay. Set disassembly flavor intel. Now I can actually read this. So we're gonna call puts. Let's. Oop. So that's actually be expected, right? Wait a minute. What? Okay. So the number of these we're going to start is 1, so I don't have to deal with the multi-threading stuff. We're going to break on thread 1, run. We're also going to set disassembly flavor intel /20i rip. Fin. So we have some A's. That seems pretty reasonable. Now what? Disk/I rip. So we pop R15. We then move that into R10. So x/x $R10 points at our A's, which seems reasonable. So R10 points at our A's. R14 points at our big buffer. We set up R13 and R11 to be limit and sweep. We then write R10 into R13. That seems fine. And R10 is a pointer to the heap. Whereas R13 oh, right, because we used I didn't finish explaining that, did I? So R14 is where we did a malloc of 21,000 hex bytes. The reason we did that is because we know that that's going to be backed by mmap, and so we just get this big ass region of memory, which we know will be page aligned. So that's good. Well, probably good. So we write that into there. We then move that into R8. We then write that to R11. We clear out R12 and RSI. Not sure if that's going to matter, but RSI is 0. R12 is 0. That seems fine. We're now in start loop. So to start this, we take what is in R13 and put it into RDI. And that means RDI is a pointer right now. We're making sure that that pointer is below what is at R11, which is right. x/gx $R11. As long as RDI is less than that, we're fine, which it is clearly always going to be. We then jump, we get here. We're then going to read from that into RAX. So RAX should be 41414141. We then move that into RDX, which is fine. We shift that over by 10. We move that into RBP. We then load an effective address. We then knot it. We then write RDX into R13. So R13 should be the point. Oh. Well, that explains a little bit, right? So x/gx R13 is currently the pointer to our string. And RDX is some random ass memory address. We then move that, compare. It's not a memory address, that is. Do we still have that? No, we don't still have that. Print that shifted by OXA. Print slash x. That's still not what I thought it was going to be. That's times 8. Print 2 divided by 8. I don't know what I'm doing now. Okay. So keep stepping. This time they don't match up. Or we wrote to it and changed it. So let's think this through a little bit. We want to trigger something weird happening. However, it appears that the way we were messing with our thread here, that's not going to work. Why did we end? Right, because we eventually hit that. So what's the next thing that we have to do here? So we need to make this line up so it doesn't crash on us. Is RAX modified? RAX is not modified. Why are we ending? Hello, Mikko. Thread 1, run. Disk / I rip. Fin. So what we're doing here is we're just running through this, and we should see eventually we're going to hit end. Oh. So when we did a test RSI, we ended up finning. What is RSI? RSI is 0. Oh, we want it to be non-zero? I can do that. Block 2. How did this happen? Somehow RDI became 4 and 4 and 4 and 4 1. Only place RDI is set is from R13 at start loop. The value at R13 is written at line 59. with, with RAX. And RAX... Wait, no. R13 is... Oh, R13 is written there. Oh. Right, because R13 is a pointer, not... Okay, cool. So this code at least doesn't crash now. Now when we start up a bunch of these... When we start up 2 of these... Okay. We're in block 4, so we did the compare RDX 200. So why did this fail? So RDX... RDX somehow became 200 again, which is awesome. So one thing that is possible is that I just don't know what I'm doing here. Pound define start OX42. Huh. Okay. So I guess these need to be odd. I guess we can live with that. Two threads. And 2 threads says we're fine. And 8 threads says we still work fine. So the reason we're sticking to 8 threads here is because now that we're multiplying by 2, it means that capital O is our last value. And because it is, that and, so the and is doing and for F. So 8 threads means that at least 2 should end up on the same thread. And if this is doing anything like what I think it should be doing, we should see this hitting something dangerous. Like, So what I expect to see right now, so let's step back a little bit to what the Errata says. If we use the AH and the REX registers in a tight loop under complex microarchitectural conditions, something should happen. Let's think for a minute about what that sounds like. So if we used, what could this look like? I think one of the best theories I've heard is that and this is going to go way deep into Intel CPU errata, and I am quoting, like, this is third hand from somebody who knows optimization way better than I do. But the short version is the AH, the high registers, the AH, BH, DH, CH registers are have a prefix. You use the rep prefix to access them. However, unlike other prefixes, so when you use the rep prefix to access the high registers, you do not get a performance penalty for them compared to accessing the low registers. But all of the other rep prefix stuff incurs a 1 cycle penalty. And again, I am repeating what Falk told me, so I may be entirely wrong about this, because this is from memory from a discussion I had several weeks ago with somebody who understands optimizations and processor internals way better than I do. But the short version is that the rep prefix to use those high registers doesn't incur the penalty that it should, which is supposedly odd. So the theory he had was that basically what's happening is that under certain situations, the CPU instruction cache, like the branch prediction or something, isn't swapping back properly when you use it. So the short version being, let's say I do this and if I do it at the same time that I swapped, like right when I'm swapping to another thread, I might not restore some of the registers properly. That was the theory, at least. But this doesn't seem to be doing that. Aren't 8-bit register accesses now emulated in Skylake? I have absolutely no idea. As far as like the CPU internals go, I have only a very faint idea of how they work. Like, at least to... So one thing that comes up a lot with like computer stuff is everybody has some sort of an abstraction. And for some people, that abstraction may be really high up. The lowest level of abstraction they understand is Java or PHP, or maybe even higher than that. They understand Windows and nothing below that. And for some people, I doubt this person actually exists, but in theory, there is somebody who understands from that level of abstraction all the way down to transistors in a processor. But for most people, you stop at some point and you might have a vague idea of how things work below that. And the point where I stop personally is instructions. Like I can read and write assembly reasonably well. And anything below that is kind of magic and I don't understand it and it's weird. So my thought here was that by going through this and poking at this errata, I'd learn a little bit more about it. Because there are things like that. Like there's a whole field of processor optimization stuff that I kind of vaguely know about. Things like most registers are fake registers now. At least this is me talking completely out of my ass from things that people have told me, which may or may not be accurate. But that basically, with modern CPUs, your pipelining stuff means that you a lot of the time will have multiple copies of different registers. So you have, like, I have REX. I don't have one REX. I might have 3 REXs because it's getting used on both branches. Huh. What if that's important? So, what if we need on the other branch to mess with some of these registers? So what is our current other branch doing? Let's kill this. We're probably not going to crash now. So we reload RDI. And we exit. RH should still be the same thing. And so I'm doing these pushes here just because I want it to hit memory. And at least my understanding is that by hitting memory, it's not going to be able to go past that prediction. So at least my thought here was that maybe I need the other branch to mess with those registers. So in this case, I'm making them clearly invalid memory. So we should trigger this if it was happening. So if it's related to branch prediction, well, let's do that too. Instead of an int3, jump and jump end. So now the other side of all of those branches. What? Now the other side of all of those branches is messing with RDI and RAX. I think that worked. Like, there's no way we should be getting a floating point interception here. I mean, unless I fried my CPU. Oh, really? Tell me more. Holy crap, it worked! What worked? I don't have the slightest clue what's happening here. Just to make sure here, I'm not crazy. There is no way that we should end up on a misaligned instruction like this, right? Like, none of our threads should have this happening. Because we have no jumps that would work that way. They are all static jumps. We jump to end, we jump to end, we jump to end, we jump to block 4, we jump to end, we jump to block 5, we jump back over to the start. but now we end up hitting it. Okay. That's what the Reddit thread, that it's a misalignment issue. A misalignment of what, though? Like, when I read through that thread about it, I thought somebody had speculated that it was a misalignment of the registers table. So there's going to be a table in memory, not memory, but the register. I don't know what to call it. There's a table of register values, and that'd be a misalignment of that. Make sure I'm not crazy here, right? So if we don't, I'm not crazy here, right? Like, we let this run for a little while. We talked about this, and I said, oh, it's going to be a branch prediction thing. What the crap is going on? Okay, we have main here. Called puts. Where do we call? Set up memory. We then call pthread to create with use.ycombinator.com. So I am getting a 403 bad request if I try and go to that. Or, sorry, 400 bad request if I end up trying to go to that. This link. 463, yeah. I think I'm going to the right spot. To the Googles, cite that function and I hate how they do things here. I don't know. I don't have a better suggestion about how to do this, but 31277. Why on earth did this work this time? Yeah, so I read through this, and I'm not sure what to think about it. In that, at least some of the there's a lot of conflicting information in this thread. This is by far the best like write-up that I've seen. But other than that, I don't. So, oh, I should move this so other people can actually read it with me. Copy, paste. Okay, I can't figure out why that link didn't work the first time, but they're nearly written out of existence. It is called out to not use them as they are emulated and not directly supported in hardware. Yeah, so I remember having read through this, and the responses to this comment are concerning to me. That, like, this person is claiming that that is, like, maybe entirely wrong, that... I don't know. In any case, I definitely feel like I'm taking greasy pills here, because we definitely saw this not working, right? Now, let's switch this over so that it's back to... Nope, that one. Nope, that one. Back. So... this version of it runs and 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 runs. And runs and runs and runs and runs and runs and runs and runs. So this totally isn't crashing. Oh, it finally crashed. Okay. So did I just not wait long enough? So supposedly, their test case could take many, like, it could take 10 minutes to trigger. So maybe I'm just impatient and awful. Int 3. So this is, we've now gone back to the int 3 version of it. So the version that we saw problems with, we would jump to end if we failed any of the conditions that should never be able to fail. It doesn't matter what the other side is, as long as it's not an int 3 is what it's looking like. Of course, I can't even say that because, you know, we have to sit here and wait for this to happen. So let's talk about what's actually happening here. So we end up, when we get to floating point exception, in the middle of block 5, like 2 instructions into block 5. So when we have an int3 there, yeah, so the version that immediately crashes, well, it doesn't necessarily immediately crash, but it quickly crashes, is this. 1, 2, 3, 4, 5. So this is the only change we have here is that the version that doesn't crash is an int3 in the failure case of the conditions. There's only one condition here. The only condition is... Oh, come on, don't do this to me now. There we go. So the only condition is this one right here. Or block 3. So I should be able to do this. This should still crash. Because there's no way their branch predictor is saying there's an unconditional jump. What's on the other side of it matters. Like the next instruction matters. I can't imagine that's the case. Oh. But I didn't think about this one. This is 2 instructions, and int3 is 1 instruction. What if it's still failing? It just happens to fail in a way that doesn't matter. So with this, the jump end and the int3s should be the same length. Why isn't it reproducing? I'm kind of stumped here. This is not how computers work in my head. Putting int3s after an unconditional jump should change literally nothing. Oh. So the idiv is block 5 plus 2. It's the middle of that test RSI instruction. So if we do we're on this idiv. So it should be a test RSI. Instead, it's turned into a idiv, whatever that is. idiv B. So this changes the alignment a little bit. So this does not appear to be triggering it. So we're going to let this run for a little bit. So this is jumping backwards, right? Hmm. So this is in fact triggering it. This is not. Let's assume this is not triggering it. But this does. Putting the second int3 there matters. And doing so so weird. Well, we can trigger it now at least, right? What is that instruction? Oh. Really should remember to do that better. Like, forgetting to remove core files is the worst. Okay. So we are in fact ending up in the same situation here. Although... Oh. AT&T syntax is so hard to read, and I don't understand it, and I was sitting here trying to figure out, why would dividing by a memory address ever cause a problem like that? And the answer is because it's not divided by a memory address, it's dividing what's at a memory address. When is that IDEV ever getting a 0? See, that's exactly what I was doing. It isn't. It's that's AT&T syntax. It's dividing by what is at RDI minus 4D, which is... I don't... Why would you ever have AT&T syntax be the default? It's the worst. Nobody likes it. So, that works. Somehow we're actually corrupting the program counter here, which is not something that I expected to ever have happen. Like, I was kind of expecting this. So, let's talk about what we have here for a minute, right? So, one, the crash we're getting is very reproducible. We are somehow jumping to a address that is just clearly wrong. Two, the registers look pretty reasonable. Like, REX looks reasonable. RCX we don't touch. Our DX is 100, which I'm not sure should be correct, but we never really figured out how that was supposed to work. RBP is weird. The stack looks like a stack. R8 is what we set it to. R10 is what we set it to. Like R11, R12, R13, R14 look pretty reasonable. And R15... Oh. Oop. R15 is that. Okay, R15 is valid.
I was thinking that R15 looks a little weird, right? Like, that seems a little off, but apparently it's valid, and that's the pointer we wanted there. I can't complain too much. Hmm. I'm trying to think of where to go from here now. We have code that can reproduce this. We don't entirely understand how to reproduce it. Like, I don't... Yeah, that is an option. So one thing I was thinking here... Wait a minute. EBO2 is going to go to CO. Instead, we're doing what is equivalent to EBO4. We're not. So... if we're... Here, I'm gonna... Oop. Ugh. Oh, I've broken everything now. Well, I guess we're living with this. OX4007CO. This is where we're supposed to be landing. Right? So the jump here is OX4007B2. That's a jump. Now, the jump here is the jump that so we don't know which one matters, right? And somehow we're jumping 2 bytes later than we should be. Or we're not. So none of this is what I was thinking. Like, I was kind of curious here if... So one of the thoughts I had here was the way that we address the AH register is we use a rep prefix. So come in here. It's this 80 right here. The 80 is a rep, or not a rep. Is it a rep? Rex. Rex. That's the thing I'm looking for. It's a Rex prefix. To address other registers. So what if we were one instruction off? That basically what was happening is because of this, when we ended up going down the jump, we ended up one instruction off. That doesn't seem to be the case, does it? So all that seems fine. So yeah, we can totally do that. So this, we just added 60 knobs in the middle of our loop. So we are very much no longer a short loop. So we'd expect this to never crash. Which seems pretty plausible. What I also want to do here test jump. So we were doing +2, right? So what I would expect to see here is if for whatever reason we're just jumping to +2 here, we should get a trap breakpoint. I think this is reasonable amount of time to say that this is not triggering, right? We added in 60 nops, and this seems plausible that it's not reproducing. Oh, right. Oh, no, you can't see this. Never mind. Yeah, I'm going to buy that that is not reproducing now. So this, I expect to see a trap breakpoint in a few seconds. Yes? No? Hmm. Oh, maybe, yeah, maybe that isn't the best example. because we've now actually changed what our we changed what our branch predictor state would look like when we did that, because now we added an extra jump. So this should crash. You're supposed to crash. Should crash. I'd be really sad if this stopped crashing for some reason, because I'm almost positive this is the same code we had that was crashing. This is why this type of bug will drive you absolutely crazy. Like, oh, yeah, it crashed. There we go. I'm sitting here going like, oh, what if I messed up? Like, what if it's that my processor's getting too hot? What if it's my processor's going bad? But no, I just didn't wait long enough. Now what? So we have verified that it is based off of the start of this, right? What's like a... make it crash faster with only 2 threads. I should be able to... I don't think it would crash faster. Because doing so isn't going... So right now we're starting up 8 threads across 4 processors. So it should be the equivalent to 2 threads on each core. I guess that's how it should work. Why are you struggling so much right now? Okay, I want to come in here. Let's do a move rat. So if I do a nop, move ALCC, we should see it. So if I have even the slightest clue of how this is working, if it's based off the... It's going to go 2 instructions into block 5. What I would expect to see here is for us to get a breakpoint. Get a sig trap. Should be getting a sig trap. A trap. So I'm not sure about... I don't think it'd be faster to do it that way. It might be worth investigating. But I would think doing it this way should work. Why is this not failing? Oh. 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 It's like, segfault? That's not what I expected to see here. So the reason I'm doing this, right, is because a push RAX is a single byte opcode. So what I expect to see here, I expect to see a sig trap.
It's a trap! It's a trap!
That thing. Oh. So, where'd you go? Close this, discard it. I want to reopen this. Come on. Reconvert this. Okay. So what I'm hoping to see here... Oh. So what I was thinking here is, what if we're wrong that it's not based off the start of block 1, it's that it was having to backtrack. It was saying, the branch predictor has said we should be going down this jump greater than loop. We now want to backtrack to where we were before, but it's recalculating that rex prefix again. So instead of going to 400C75 like it should be, it's going to 400C74 like it shouldn't be. But it's not doing that. What if we align it better? So we've now returned to the same alignment we had before, where we'd previously had the jump greater than at C4, was ending up at C3, I think. No. No. This alignment might not work either. Because it was ending up at C2. Which, I mean, yeah, sorry. I keep switching between the disassembly and this, and I keep not switching the window back. So what I should do is do this, and then move this window like this, so that even when I forget to, we can still see things. But this still isn't crashing on me. Like, I expect this to segfault. Why won't you segfault? Well, I don't expect a segfault. I expect it to hit a sig trap. And we're not. Well, let's make sure it isn't this too. Hmm. So, this doesn't appear to be crashing. I think at this point, we've been going at this for over 2 hours now, so I think this is probably about the time to start calling it wrapping things up. Because I'm not really sure where to go from here. I think the right answer is, this is interesting. I think we need to think a little bit more about what we're doing. We can trigger it, which is a huge step. We can actually trigger things happening that should not be happening. Actually, before I make that claim, we have this. I swear, if you stop crashing on me, I will beat you, computer. If this doesn't work, I will be kicking you. Yes. If you follow me on Twitter, I will look into tweeting out something about this. If not tonight, then tomorrow. At least like something on GitHub. Like was it a gist? Why do you hate me, computer? Why must you hate me so much? So the good news is that there are relatively few systems that have patched this, as far as I know. At least when we started, as of when we had started this, Debian was the only OS that had pushed out patches for it, at least that I was aware of. Anything else you had to do manually. I think like Debian and like Red Hat maybe, but it was not widespread at the very least. So it's possible that since then more places have pushed it out, but I know as of when we started these streams about a month ago, Windows was not patched and Ubuntu was not patched. So you may be lucky there. Oh, right. We expect this to crash, right? We messed up the alignment, which is what was happening there. So this should crash. Okay. Why do you not crash? Please crash. So while we're waiting for this to crash, I I guess there's a few things that I had... oh, there we go. So this crashes. Actually, before we do this, this crashes. If there's only one core, this should not crash. So while we're waiting for this to run through and demonstrate not crashing, things that are important. So next week I plan on streaming Monday and Wednesday, although Wednesday is probably going to be a very short stream. I'm flying out to Vegas first thing Thursday morning for DEF CON, so like first thing, like 6 a.m. first thing. So I probably will not be streaming particularly long next Wednesday. Well, so the version, I have a version that crashes that is checked in right now, so I think I'm good. But yeah, so next Wednesday is going to be a short stream. Next Monday, I'm a little torn on what I'm going to do. I think it's going to come down to, I'm going to spend the time between now and Wednesday thinking about this and trying to decide where to go. Because we can reproduce this now, which is great. Yeah, I should set the... Well, so that's the thing, right? What I'm testing here is that a single thread on its own does not trigger this. Which means there is no way that under normal operation, unless there were problems with the threading, unless we're hitting this bug, we should not be crashing. That there's not like some subtle bug in the code I wrote that's causing this. That's what I'm hoping to rule out here, is that like if I sit here and I talk for another couple minutes about stuff and this doesn't crash, then I think it's safe to rule out that there's some bug in the assembly that I'm looking over and not seeing. But yeah, so next Monday, I think we might continue with this, but it depends on what kind of ideas I can come up with between now and then. If it's going to be the same, it's going to be the same thing, like looking at this and going, huh, I don't know what's going on here. Huh, I don't know what's going on here. Then I don't think it's going to be particularly interesting to do another stream of that. Like, I think... At this point, I'm not entirely sure where to go. Like, I'd like to try and figure out exactly what's going on, and at least ways to manipulate it. But until I can do that, I don't want to do another stream on this. Because we've done enough that kind of we're spinning our wheels on it. So, hopefully, between now and Wednesday, I'm going to come up with a good idea for ways to proceed. If I don't, the backup plan is to work on what I was doing last night. So, for people who haven't been following me on Twitter, I set up a second channel for non-technical stuff. So for things like video editing, messing with Photoshop, doing things like that, like they're not technical things. So anybody who's watching this because they want to see, highly technical details, like poking at, my processor and seeing what happens, probably are much less interested in, I'm poking at Photoshop and trying to make a picture look decent. However, there is a different group of people that might be interested in that. So my thought at least was, I might as well put that out there so people have the option. So I now have there's now a second channel. There's a link to it on the YouTube channel here, if you want to take a look at it. And last night I was streaming, trying to set up a OBS setup for the Magic Online client. So when I have free time, sometimes I like to play Magic the Gathering. And at least my thought on it is, if I'm going to do it, streaming it sounds like fun. Like, I'd like to get input into my play for it, so I might as well go out and stream it. And I started setting it up, and it failed completely. It turns out OBS is unable to capture the window for the game. Like, it can't see anything. And the only way to do streaming of that game is through an entire display capture. And the reason for this is because it's kind of a, really weird .NET game that does a whole bunch of bizarre stuff. So at least my thought here is, if I'm not doing anything interesting with this, I might take a little while and poke at that. So look at how OBS does its window captures, and then write some code to look at what kind of data is being received by that, look into like the Windows API for capturing windows, things like that, and see if we can't get it working such that I can actually capture stuff from a window. Because I think that seems somewhat interesting, and is hopefully something that we can get some progress on in only 1 or 2 streams next week. So that's a backup plan. The primary plan here is, screw that, I have a good idea for tracking down this Intel bug and doing something interesting with it, so we're totally going after that one instead. But we'll see. That's going to be next week. And then the weekend there, afterwards, so I think it's 27th, 28th, 29th of July, is DEF CON. I'll be in Vegas for that. It should be a lot of fun for it. If people are going to be in Vegas and want to say hi, getting a hold of me on Twitter is probably the easiest way to do it. I should have the Twitters with me and be able to do that. After I get back from Vegas, though, I want to try something different. I've talked about this idea for a little while now. I've been throwing it around, and everybody I've talked to it about has been super excited. It sounds like a lot of fun, but I wanted to get some other stuff done first. So the idea for the next series after this, like the next major series of streams, is going to be what I like to call a history of Windows bugs. And the plan is we're going to start with Windows 95. I'm going to get a Windows 95 VM, get it fully patched, get whatever version, the highest version of IE that's going to work on that is, get all of that set up. And then we're going to get remote code execution on it, a IE4 or whatever browser bug, do whatever privilege escalation we can do, things like that, and basically use modern tools to find bugs in Windows 95 and work through all of that. And assuming that works reasonably well and people are interested, after that, move on to Windows 98, and then ME, and so on. I suspect by the time we get up to like XP and Vista and things like that, finding new bugs is probably not something that I'm going to be doing on stream. Like, I am relatively okay with, here is some Windows 95 O-Day. Have fun, guys. If it's, Windows 7 O-Day, I probably don't want to do that on stream. So at some point, it would switch to, here is a recent CVE for the system. Let's try and land that. At least the idea would be to have a, like, here are remote code execution and browser bugs for versions of Windows from 20 years ago up to today, or, a couple months ago when the last major bug came out. And at least I think that'd be interesting to do, especially if we bounce back and forth. So do Windows 95, and then let's look at a recent CVE on Windows 10, and then do Windows 98, and let's go find a Windows 8 CVE and take a look at that, and back and forth like that to kind of balance things. I think it's interesting, and that's the plan for when I get back to Vegas to set that up, to start with Windows 95, because at least my assumption here is that even the last version of Windows 95 that was shipped is still going to be absolutely terrible. We turn on a few services, we just run a fuzzer against it, and it goes, oh look, you now have full code execution across the entire system. You sent A's into a random port, and EIP is 4 and 4 and 4 1. That's kind of what I expect to happen. We'll see how hard it is. But hopefully that's going to be the plan when I get back from Vegas, is we're going to find some Windows 95 bugs, we're going to get some IE4 bugs or whatever it is, and we're going to land those. And hopefully it's going to be a lot of fun, because while I've done a little bit of Windows exploitation, I definitely have never done Windows 95 exploitation. So we'll see what goes into actually making that work. And hopefully it's amusing for everybody. If it isn't, we'll figure something else out after that's done. That'll probably take us through most of August at the least to get a whole bunch of Windows stuff set up and actually landing bugs and doing interesting things. So, I think it's about everything. It definitely looks like the single thread version is not crashing, which seems like it's a safe assumption that the code we're running here definitely is triggering the Intel CPU errata, which is super exciting that we finally managed to trigger that. It is really confusing about how we're triggering it, because I did not expect us to end up with PC pointing at something that is not a valid instruction. Like, I was expecting, oh, RDI is the wrong value, or, oh, we copied RAX from one thread to the other thread. Like, that's what I was expecting to see by this, not PC is off by 1 or off by 2. So that's exciting. It's also confusing and hard. So, in any case, hopefully this was interesting for everybody who tuned in. If you have any questions, comments, thoughts about it, the easiest way to let me know is to message me on the Twitters. Otherwise, leaving a comment here should work. As soon as I end the stream, the regular comment section should open up. And other than that, I will see people on Monday. And thanks again, everybody, for tuning in. Bye.